Hello, welcome back everyone. Assalamualaikum. So today we're gonna do discussing again, um continue for practicing the real question of ACS exam. So let's get started for the first question. So we are still dealing with, like, we are still in the topic of state of matters. So including the gas and liquid or solution or and solid. So this chapter cover, like, a wide range of the subtopic. So we have to, like, learn about gas or liquid or other stuff. Okay, so let's solve the first question. Which sample deviates most from ideal case behavior? So remember that the ideal case, okay, ideal case need to have what? Okay, need to have what? So the key concept of ideal case is no intra, okay, no intermolecular force. This is the first one. Okay, no intermolecular force, and then particles take up no volume. So there is no volume. Okay, there is no volume. And then the real case, okay, real cases is uh attraction. Okay, attraction. And then take up space. Okay, so in this case, what we want to know is, like, which, how to get this one, no intermolecular force, by, okay, by lowering pressure. So when we lowering pressure, okay, it will, like, give the less kinetic energy, right? So attraction, like, so attraction, oh sorry, by mm, wait, so yeah, lowering temperature, not lowering temperature, low, sorry, it should be lowering temperature, not pressure. If we are lowering temperature, okay, it will give the less kinetic, okay, less kinetic energy. Okay, less kinetic energy. uh let's take a look at the one that we already done for concept. See, low pressure, far apart, okay, less attraction. So low pressure, like I mentioned before, to get the ideal case, sorry, to get the ideal case, lowering pressure, okay, lowering pressure, so it will uh far apart, it will far apart, and then like lowering the attraction, right, less attraction. And then we have to have again high temperature. If 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 uh if we apply high temperature, the particle will have, like, the particle will have kind of, like, very fast, like the will move very fast, so fast, so there is no time to attraction. Okay, there is no time. Okay, so there is no time for attraction. So how to get the ideal case? High temperature, so no time for attraction because they are moving so fast. Okay, so in this case what we want to get is deviates. Okay, deviates most from ideal case behavior. So we need to take a look at, like in this case. Okay, so like high pressure and then low temperature. If we have like high pressure, particle are close together. Okay, high pressure are close together, so more attraction. Okay, if we are lowering temperature, the particle will have like less kinetic energy, so there is attraction matter over here, right? So there is attraction matter over there. So in this case, we need to take a look at which one that has which option has high pressure. Okay, so we can eliminate this one because the xenon at 1 atm is like lower temperature. All right, now let's move on to which one that lowest temperature. Okay, lowest temperature, so between B and C, right? We can eliminate for option D, right? So um we need to consider once more thing, what it is. So which one that a bigger? Okay, which one that bigger? Let me open the periodic table first. Okay, so in the periodic table, as you can if you look at the periodic table, helium and xenon. Okay, yeah, xenon it will have a like a bigger size rather than helium. Okay, bigger. Okay, so if they helium is small. Okay, helium is small. Okay, so if in this case, so we can see this one, it will be like less deviation. Okay, because this one is small. Okay, small, which mean, okay, it will have like much more a bigger gas deviate more than small one. Okay, so xenon will be the bigger one. So bigger gas like xenon deviate more than small one. All right, so remember, bigger gas, it will have more deviate. More deviate. All right, so as you can see that ideal case assume no intermolecular forces. If we have particle take up no volume. If real case, like which one that more? Okay, bigger is more. Yes, because uh it will have less kinetic energy. You know, um, bigger, it will have less kinetic energy. Less kinetic, so attraction matter. Okay, attraction will matter. Okay, remember this one. Okay, bigger, so it will like has like moving slower. Okay, then the small one, and then the attraction is matter over here. Okay, so the answer will be B. Okay, again, all cases approach ideal behavior under condition of low density and high temperature. As you can see, we have to know the condition of ideal case. Remember, the ideal case have to have, okay, the ideal case have to have conditions such as lowering pressure, okay, lowering pressure, so less kinetic energy, lowering pressure, so it will far apart, okay, and then there is no after that there is no attraction, and then it should be like high temperature, so no no time for attraction, okay, no time for attraction. If we have like bigger a bigger size, it will have a lower speed, so there is still like a bit space for attraction each other. Okay, so all cases approach ideal behavior under conditions such as what? High temperature, yes, because there is no time for attraction. Okay, there is no time for attraction. Low density or high density, the question is about density. Okay, as you know that the density related to the volume, okay, rho n per v, mole per volume. So volume is n per rho. So inversely, volume is inversely proportional, inversely proportional with density. Okay, so the conclusion of this case is we need to have a bigger or lower. We have a bigger or a smaller size. We need to have the smaller size. Okay, we have to have smaller size. So smaller size telling us that we have to have like small volume, small volume. Okay, smaller size, smaller volume, and then small volume, so we need to have like higher density, sure, the answer might be C. Let me check why. Oh, okay, so the concept is not like that, so I'm made the mistake over here. So to minimize interaction, make the gas is close to the ideal, okay, we need to have a low density. Okay, low density, so particle are far apart. Oh, okay, low density, far apart, so less chance to attract, to interact. So the answer will be C. Hey, yes, low density, not the high density. Yeah, this should be correct. We can use the previous concept. Yes, that's true. The previous concept is volume we want to low. Oh, yes. So it will be incorrect, the previous concept. Okay, just remember, just for quick recap, okay, for ideal case, okay, remember for ideal case, we need to have the behavior such as what? Lowering pressure, okay, lowering pressure. So it make the particle like becoming far apart, so less attraction. All right, and then we need to have what again, like high temperature. So if we have like high temperature, there is no time for attraction. Okay, and then the next one is smaller is better. Okay, smaller is better. I mean, it close to the ideal case rather than the bigger one. And then less density is good because it will be like it will far apart. Okay, it will have the characteristic such as far apart. Okay, less density, so it will be far apart. So we minimize the interaction. All right, so that's good. Now let's move on to number 3. What is the density of F2 at 180 m and 25 degrees Celsius? So, like I mentioned before, we can use the P the density is rho, okay? And then this is RT, right? And then this is PM. M is smaller mass, okay? So we can use this one. Just remember the concept of this one. 180 m, the R is 0.0821 times what? Times 298. Okay. And then molar mass of F2 is 38. So the answer of this one is 38 divided by 24.5. So the answer will be 1.55 gram per liter. Okay. Yeah, all right. We can pause this one. Okay. Yeah. Hmm? Okay. All right. So let's continue our discussion again. So just remember this equation, okay, to find out the density of element. All right, and then number 4, a 14-gram sample of N2 in gas phase occupies what the volume at 0 degrees Celsius and 1 atm. So the question is about the volume. Okay, what volume? We can use the PV and RT, right? So 14, okay, divided by N2. N2 should be 28, right? And then R 0.0821, and then T will be 273 Kelvin, right? P will be 1 atm, and then we have V. So just this one 0 point. So after we calculate all of them together, we ended up getting around, wait, I just wanted to writing down first. So it's around 11.2 liter. Yeah. All right. So the answer will be B. All right. And then now let's move on for another question for number 5. Which gas is most dense at 2 atm and 400 K? So let's take a look at this question by using the formula PV and RT. Okay? using this formula to solve this problem. Okay, can we do it? Yes. You need to know that P is what? Oh, sorry, most dense. So rho, P, M, and R, T. Okay. So in this case, R and T will be same, right? P and then P also same. So we can cancel out. So rho is proportional with the m or molar mass. So which one that has the highest molar mass? The highest molar mass. F2 is only 38, right? N2 is only 28, and E 20, and then O2 32. So which one that the most dense? It should be A. Okay, because like I mentioned, density is directly proportional to molar mass. All right. Number 6. In 10-liter vessel at 100 degrees Celsius, 10 gram of unknown gas exert a pressure of 1.13 atm. What is the gas? The question is, what is the gas? Okay. So to solve this problem, we can again using this formula. Okay, using this formula like rho PM RT. However, we have the liter over here. Okay, we have a liter over here. So what we're gonna do is pretty simple. Okay, so what is the gas? We need to know the molar mass. Okay, the molar mass. So we need to know the molar mass. Okay, now let's using just PV and RT. Okay, we have like 100, so 100 plus 273, right? 100, so 373. R is 0.082, right? 0.082, and then N, what N is here? So we need to get the N, right? Yeah. And then P is 1.13, V like 10 liter. So we will get N at the end. So after like calculating all of them, we ended up getting like around 0.369. So let me take a look at 0.082 times 3. Okay, divided by okay, and then divided by again 10. Let me calculate again. 0.082 times 3, okay, divided by hey, sorry. So N is 1.13 times 10 divided by again. Yeah, this one, N, right? So now let's try to get the mole. I mean, we have mole. So we have the information of gram, and then we have like molar mass after that. So molar mass over here, 10 divided by 0.369. So the answer would be let me 10 divided by 0.369. So it will be 27. So HCN. Right. That's great. So now let's move on to another question. What happened to the volume of fixed amount of gas if both pressure and absolute temperature are double? Okay. The question is, what happened to the volume? What happened to the volume? So I just want to double check. Number 5 is A, double number 6 is B. All right. What happened to the volume of fixed amount of gas if both the pressure and absolute temperature are double? You know that the PV and RT, okay? What happened to the volume? The question is the volume. Fixed amount, okay? This is fixed. If both pressure, where's the pressure? This one. And temperature are double, okay? If temperature are double. So you see V, we can cancel out the N because it's constant, R also constant. And then we have T and P, okay? So if we doubling to T and doubling to P, so it will be same T and P, so no change. Okay, so no change. A sample of gas occupies 3 liter at 1 atm. What volume will it occupy at 1.45 and the same temperature? Okay, if we have a gas like using PV and RT again, the question is volume, right? So R is 0.082, and then a sample gas. Okay, let me think first about this. A sample of gas occupies 3 liter at 1 atm. So what volume will occupy at 1.45? Oh, okay. So just using this one, PV and RT, and then PV and RT. Okay. So the question is volume. 1, 1, 1, 1, 1, 2, 2, 2, 2, 2. So T is same, right? R is same. And then how about the N? N itself is same, right? There is no change over here. So we have ended up getting P1, V1, P2, P2. So if we have like 3 liter and then 1 atm, and then we change like here like 1.45 atm and then V2. So what's the volume of V2? Let me calculate. So 3 divided by 1.45. So it will be 2.068. So it will be A for the answer. Yes, that's true. What volume of oxygen gas measured at blah 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 produced from the decomposition of blah blah blah. Okay. So now we need to find out or looking for the answer of the moles. Okay, moles of HGO. Okay, HGO. Okay, we have like mole HGO 67.5 divided by 21659. So it will be 0.3116. Okay, so if we doubling this one, so in this case the coefficient is 2. The question is what the volume of oxygen. So oxygen is only 1, so mole of oxygen just divided by 2, so is 0.155. Okay, right. And then what's the next thing here? So we know the mole, right? And then what we're gonna do is what the volume. Okay, what the volume? Okay, we can use the PV and RT volume. So N is 0.55, R is 0.082, T is what? It's 300, And then P is what? P is 0.987. So times 0.0 divided by 0.386. Okay, the answer will be P. Yes, the answer will be P. Yeah. Okay, that's great. So we understand how to solve this problem. And then let's move on to another question again. What mass of solid aluminum is needed to react with the excess sulfuric acid to produce blah 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 blah? Okay, let me. Come on. We need to look at the information in the periodic table. Okay, why is the boiling point PR2 is higher than Cl2? Cl and then PR. Which one is bigger? PR is bigger, right? Okay, PR has greater molar mass, is therefore easier to vaporize. Okay, why the boiling point PR2 is higher than that of Cl2? This is the great question, because we need to understand the concept of the vaporization. Okay, PR is less electronegative and therefore its bonding is more ionic. PR is more electronegative, more electro. So if we are looking at the electronegativity, okay, PR is both non-polar, right? So not ionic. Okay, PR more electronegative. Okay, if you are looking at the electronegativity, right? Electronegativity from left to right, it will be increased, and then from top to bottom is decreased. So PR will less electronegative. So this one is incorrect. Okay, so based on this information, we know that PR is more electronegative is incorrect. Yeah, udah. Apa, Bu? Iya, telepon. Telepon ya. Iya, ayah lagi ngajar. Iya. Okay, why is the boiling point PR2 is higher than Cl2? Okay, PR is bigger and PR is less electronegative. However, this is not ionic bonding. This one is non-polar bonding. With Br and Pr, we know that it should be like not ionic bonding. Okay, so not the answer shouldn't be B, right? And then how about the option A? Pr2 has a greater molar mass, therefore easier to vaporize. If we are saying easier to vaporize, so it will have lower boiling temperature. Lower boiling temperature. So should be not. Okay, it should be not. This contradicts the equation itself. Okay. Now we only have option D. Pr2 is more polarizable, therefore has greater London dispersion force. Okay, more polarizable, so stronger dispersion force, therefore higher boiling point. So what does the meaning of the polarizable? Okay, polarizability is how easily atom or molecules electron cloud can be distorted. Okay, so small atom like helium, chlorine have thick compact electron cloud, so hard to distort. However, like larger atoms such as bromine or iodine have more electron, okay, and then this electron spread it out, okay, farther, easier to distort, okay. Why does distortion matter here? When electron like shift around even a little, they can create temporary dipoles moment. Okay, this create instantaneous attraction between molecules like van der Waals force. Okay, the more polarizable the molecule, the stronger this temporary attraction. Okay, so because Pr2 larger, it will have like much more electron cloud, and then it will have stronger temporary dipoles, which means stronger London dispersion. So in conclusion, PR2 has higher boiling point because it's more polarizable. It's bigger and then has more electron. Okay, so it forms stronger London dispersion. So it takes more energy or heat to separate the molecules. Stronger London dispersion force, therefore it takes more energy. Okay, so the boiling point, so more polarizable. London dispersion, it will create the London dispersion, or even like dipole, like temporary dipole moment. Okay, and then it will increase the energy needed. Okay, so the answer will be D. However, if we don't know how to get the correct answer, we can eliminate the option one by one. By eliminating the option, we can get the correct answer without knowing that, okay, more polarizable, much more like creating much more London dispersion, and then creating temporary dipole moments, and then therefore it takes more energy, right? All right. So let's move on to number 21. Which substance has the lowest boiling point? Okay, which substance has the lowest boiling point? Okay, now let's take a look at the information of the molar mass first. Okay, CH4 is 16, right? CCl is 154, CPR2 around 332, CL4 is 519. Okay, so the lowest boiling point. Okay, the lowest boiling point. So imagine that if we have the lowest boiling point, which means it just take less energy to heat it up, to break apart the molecules. We just need to like to vaporize the molecule uh to make it being in the gas space, right? So we just need like a lower energy, which mean we know that the lightest one has the weakest um intermolecular force. Okay, with the weakest, like the smaller size will produce less intermolecular forces. Therefore, from here we can get the answer directly. Should be A. Okay, should be A. However, we need to consider kind of like some uh concept over here. Like what we need to know is all of them first all of them has the tetrahedral uh geometry structure. Okay, so therefore all of them has symmetrical, therefore, okay, all of them like non-polar molecule. Okay, so tetrahedral non-polar molecule. Okay, because all of them like non-polar molecule, so again London dispersion is the only intermolecular force. Okay, so more electron. Okay, so like London, and then more electron, stronger dispersion, and then higher boiling point. Higher boiling point. So because the CH4 is the lighter molecule, so it has um the weakest intermolecular force, so it has lowest boiling point. Right. Now let's move on number 22. Arrange this molecule in order of increasing normal boiling point. Okay. Now let's take a look at the formation first. Okay, LEF. So the all of them is like linear, right? It's kind of like linear. And then F2, okay, F2 is same, right? F2 is same. Okay, so we can conclude that the F2 is non-polar. Okay, okay, now the key concept is boiling point and then intermolecular forces. Okay, so now let's take a look at one by one. Okay, because F2 is non-polar. Okay, non-polar. So F2 will be the weakest one. Okay, the weakest. So the lowest boiling point. So we should start from F2. We can eliminate this one. Okay. Now let's take a look at for each for LIF, lithium and F. Okay. How about this one? Lithium is positive, right? And then fluoride is negative. So this one is metal and then this is non-metal. So it should be this is ionic. So ionic has the highest boiling point. So in terms of these molecules, there is no more ionic bonding except lithium and fluoride. So it will be LIF will be the last one. Okay, because this is the ionic bonding. So we can eliminate option C. Now let's take a look at HF and then HCl. Okay, HF and then HCl. Now we compare the size itself. Which one is bigger? HCl is bigger. Okay, so the bigger one has more electron and then more polarizable and stronger type dispersion. Okay, stronger dispersion, and then it will be having like higher boiling point. Higher boiling point. Higher boiling point. So HCl will be the the second high boiling point. So the answer will be A. Hmm? Oh, okay, okay. Sorry. Because HF is the hydrogen bonding. Sorry. So this is the higher than HCl. So it will be B, right? F2 because F2 is non-polar. HCl because it's only contains the dipole, and HF is hydrogen bonding, and then it's LEF is the ionic bonding. So the answer will be B for number 22. Yeah. Which pure substance has the lowest boiling point? Okay, all right. So if you are looking at the boiling point over here, we need to get which one that non-polar. Okay, and then we need to take a look at which one that. Okay, let's take a look at one by one. Okay, there is no hydrogen bonding. There is no ionic bonding over here. We just have information like non-polar, and then there is a indicator over here like the molar mass. So which one that the lowest one? So it should be not this one and then not this one. Okay, because the molar mass is should be the lowest one. Now let's take a look at another information rather than just looking at the mass. Okay, this one has this. This one has this one. So I remember about the longer chain. Okay, the longer change. Okay. Number 23. Which substance? Remember the hydrogen bonding is H, F, O, and N. In this case, A doesn't have any kind of what? Any kind of hydrogen bonding. Okay, we can eliminate this one. And then how about this one? B, it should be, okay, let's revise our understanding first. Okay, now let's take a look at the hydrogen bonding of each was that uh of each option. And H2, it might be it containing hydrogen bonding, right? So we avoid any kind of option containing hydrogen bonding, because if they have hydrogen bonding, which mean increasing the boiling point. So option C and D we eliminate. Okay, right. Now let's take a look at in term of the molar mass. Okay, in term of the molar mass. See, in this case, the molar mass of this one is bigger than this one. So it's pretty easy to answer. A is the answer because the smaller one, okay, has the lowest molecular weight and no hydrogen bonding. Okay, number 23 is A. Yeah. Which pure substance has the lowest vapor pressure? Okay, so we have kind of information for the boiling point. We have information about the vapor pressure. We have information about the kinetic energy and then other stuff. Okay, which pure vapor pressure, okay, at 25 degrees Celsius. Okay, now let's take a look at the information of uh this one is about vapor and intermolecular pressure of force. Okay, now CO2, H2O, H2O containing hydrogen bonding, right? So lowest one, the lowest one. Okay, just remember the concept. Low vapor, it means strong, okay? Strong IMF, intermolecular forces. Why? Because like molecule don't escape easily. So lower vapor pressure. Okay, the lower vapor pressure. So the meaning of vapor pressure is pressure from gas molecule above a liquid, above of liquid. So some molecule at the surface have enough energy escape to the gas phase. This escape molecule exert a pressure above the liquid, that's called vapor pressure. So key idea here is the vapor pressure depends on how easily molecule can escape from the liquid. If the sample has the lowest vapor pressure, which means it should be stronger IMF, right? Okay, so the thickness holding molecule together. Okay, strong IMF, low vapor pressure, which mean if molecule are highly tightly together, is harder. Okay, if the IMFs like tightly together, okay, it's harder to them to break free into the air. Okay, to for them to break into the air, and then fewer molecule escape, right? So result lower vapor pressure. Okay, so we need to find out which one that the strongest. Okay, which one that's strongest. If the okay higher pressure. Okay, so more particle in vapor, which mean higher pressure. So stronger IMF like harder to evaporate. If harder to evaporate, lowers pressure. So which one that the strongest IMF? H2O has the highest one. Why? Because it has the hydrogen bonding. O2 no. H2S no. Okay, CO2 no. Okay, not like that. All right. So now let's move on to another question. As intermolecular forces increases in enthalpy of evaporation, as intermolecular forces increase and vapor pressure, like I mentioned, if the intermolecular force is increasing, it will be decreases. Okay, why? Because it's more tight, so it's much more harder to break them into the air. Okay, and then how about the enthalpy of evaporation? It needs much more energy, so it will be increases. Okay, delta H will be increasing. So the answer will be P probably. Yes, 25 is P. The answer is P. Okay, now aluminum metal crystalline has FCP. FCP, like I mentioned, if we have FCP or FCC, is the Z itself is 4. Okay, so we can get the answer for this one like rho Z A cubic, right? Oh, M and then N A. Okay, so how to remember this one? ZM, but me GM. Okay, ZM and then NA and what else? Over here is A3. So this is FCC, right? FCC. FCC, so the Z is 4. Okay, the Z is 4. Is that right? The Z is 4. PCC is 2. So the question is how many aluminum atoms are one unit cell? So let's see. Okay, FCC at like a corner. Okay, we pause for a while. 40 degrees Celsius and boiling point of 130 degrees Celsius is as electrical insulator is soluble in water, but the resulting solution is not conducting. Based on this observation, what is the most appropriate classification of OS, like osmium oxide? So because of like is electrical insulator, it's soluble in water, but the resulting solution is not conducting. So it tell us like there is no what can it plus and minus. Okay, okay. I mean, there is no electron carry out the electricity over here. So I'm pretty sure this one is not ionic bond, ionic solid. Okay. Uh, let's go through the option one by one. Okay, this is not ionic solid because ionic solid should conduct electricity when dissolved. Okay, so we can eliminate this one. How about the covalent network solid? These have like very high melting point, like diamond and others, right? So because the melt is just 40, so it will be not. How about the metallic solid? Okay, metallic, it's indicate conduct electricity in the solid one. So it's electrical insulator. Because it's electrical insulator, okay, it should be not. Okay, metallic solid should be conduct electricity in solid form. Either as well as for ionic, okay, ionic as well, it should conduct electricity in solution form. So the answer will be D. Why? Okay. So, molecular solid like low melting point, and then it also non-conducting, and then soluble in water but no free ions. Okay, so the answer will be molecular solid. Okay, just remember the covalent network solid, it will have like very high melting point. All right. Okay, so number 28. Which point correspond to the normal boiling point of substance? Which point correspond to the normal boiling point of substance? So remember, boiling point is from the liquid to the gas. Okay. Let me see. 27 is T. Yeah. So as you can see, guys, this one is liquid, right? This is the solid. This one is gas. Okay. So to get the boiling point, boiling point is from liquid to the gas, so it should be C. Okay, the answer number 28 should be C. And then remember, normal boiling point is when the pressure is 1 atm. Okay, now let's move on. The process described by changing the system from point A to B. Okay, so from solid to liquid. Okay, from solid to liquid, it should be what? It's very easy for answer. To answer this one is very easy. From solid to liquid, it should be melting. Okay, condensation is from the gas. Okay, and then condensation being gas, right? Where is this one? What is the question? Okay. Right. Okay. So just let clarify one by one for the option. Remember for condensation, okay? Condensation is from what to what, okay? 29. Which arrow on the page? Okay. Hey, we need to okay, let me clarify. Okay, condensation is from gas to liquid, right? Yeah. And then how about the evaporation? Evaporation from liquid to gas. And then melting from the solid to liquid. Okay? And then the last one is sublimation from solid to gas. Okay. Which arrow on the phase diagram correspond to the particle level phase change shown? So see, from far apart to more condensed to be more dense over here. Okay, see? So uh probably this one is gas, and then the other one, this one probably because it's close together, condensed at the bottom, so might be this one is liquid. So gas to liquid, it's probably condensation, right? Gas to liquid, probably condensation. It should be condensation, and then or I'm pretty sure this one, it should be solid. Looks like solid, right? Okay, let me see. So, which arrow on the phase diagram correspond to the particle level phase change? So, remember this one is gas, this one is liquid, this one is solid. Okay, so from gas to solid, so it will be D, number 4. So yeah, done. So we done for all of them. Hopefully I can repeat it again so I can understand much more clear in the future when I like re-explain again. All right, it's done for today. See ya, bye bye. We will meet again for the next chapter. Okay.